Let us talk about microprogrammed control unit. So generally in microprogrammed control unit, we will be writing some code, I can say. Okay, it's not a circuit. So I can say that we will be storing the control signals in a memory. Remember it. It's all about control signals. Finally, you remember one thing. Control unit should generate control signals for for making your circuits work, right? Control signals. That control signals can be generated using circuit that is nothing but hardwired, right? If you use circuit, then it is called hardwired control signals. Second one, we have microprogrammed control signals. We can program them. Sir, why we have to program, for what kind of instructions we have to do microprogrammed control unit, we will see. Especially for RISC kind of architectures, people prefer hardwired control unit because it is simple to design. But when the instructions are CISC instructions, then the number of control signals, otherwise the complexity will be increased. That's why generally we don't design hardwired control unit. Rather than that, we go for microprogrammed control unit. In that, we will be storing the control signals in a memory. That is the idea. Now we'll see how that idea will work. So especially in CISC kind of instruction sets, the number of operations are highly variable. We can't divide the work into 5 parts. So some instructions might take 5 units, some instructions might take 10 units, some instructions might take 7 units. Example, see this instruction, a simple instruction, add R1, R2, R3. So it is a RISC kind of instruction, right? So that's why it takes only 5 stages. Correct? We can design a 5-stage system. But when you have this kind of instruction, add memory of 100, memory of 200, imagine this kind of instruction, memory of 300. Really this, what is the meaning of this instruction is easily we can predict. Go to memory of 200, okay, go to memory of 300 and fetch the operands, right, x, let's say y, then add them, okay, we need adder circuit, x plus y, then store it in memory of 100. How complex this instruction is, to execute it you need lot of cycles, correct? So this kind of instructions are generally called CISC instructions. Then you might require more than 5 stages to execute this instruction, correct? Now that's why for this kind of model generally people use, it will be very difficult because that is what experience says. So according to experience people realize that, so for this kind of CISC kind of instructions, microprogrammed control unit will be better, where we will be storing the control signals using the memory. That means we are programming the control signals. We are not creating the circuit for the signals. Okay, there are two models. Let me repeat again. We can generate control signals using circuit, that already we covered. Second thing is program it. So there will be a program which is going to generate the signals, okay, through the memory. That's why we are going to store the program in the memory. We will see that detail slowly. Now example, let's say you have, now from now onwards we don't assume any particular instruction because we are now going to talk about CISC kind of instructions. That's why, so for CISC kind of instructions, so what typical instruction might be like this: add, again I'm taking this one, add maybe R1, memory of 100 and memory of 200. First of all we have to fetch this instruction, correct? After that we have to decode it, right? Then after that remaining stuff, again we have to go for memory access, again we have to go for memory access. I can say that go for memory access, again go for memory access second time, right? Then after that do addition, right? Then after that storing. So here you can see 1, 2, 3, 4, 5, 6. 6 steps we can see, correct? Now what I want to tell you is, but fetch and decode are common. Every instruction should be fetched, every instruction should be decoded. That's why what I can say is the code for fetching and decoding might be same, right? Now assume that, let's say this instruction's fetching is like this, okay, like a RISC instruction fetch. What are the things we have to do to fetch an instruction? First of all, program counter data, whatever the address, we have to take into M address. That means we have to take in some register, which is nothing but typically memory address register. Okay, after that we have to read the memory. that memory interface will work with this memory address register. Whatever the address you show in memory address register, that will be taken by that memory interface, and it will read the memory if you issue this operation, right? After that, we have to wait for this signal. Did you remember? Already I told you, if the data is not available in cache, we have to go for main memory. That's why it might take some time. So that's why we have to wait for this signal. After that, we have to, when we get this signal, then data is available, that will be transferred to instruction register. After that, program counter should be incremented. So here I would like to tell you one thing. All these things are called, micro operations. I can say this entire thing is one micro operation. Okay, one or more micro operations. Don't worry about it. To execute one instruction, we need some atomic steps, right? Like, one step, one step, one step, in that way. All these things are called micro operations. Okay, that is enough for you. So don't go into details of micro operations. So these micro operations all together will form one instruction. Okay. Now for any instruction, the set of micro operations are same. Correct? Because fetch is same. Understand? Similarly, for any instruction, typically maybe decoding is same, but the remaining parts will vary. It depends on the instruction. For add it will be different, for load it will be different, for store it will be different. Correct? So that's why what we are going to do is, example, let's say just focus on any instructions fetch. To do this fetch of the instruction, probably you will be doing some micro operations. To do all these micro operations, we need to enable some signals, correct? Control signals. So assume that, let's say, the control signals required to do all these operations are C1, C2, C3, just for assumption. So in micro programmed control unit, what we are going to do is, we say like this: to perform fetch operation, which is one micro operation, I can say. Okay, so to fetch micro operation, we require, how many control signals we have to generate? C1, C2, C3. From now onwards, we are not going to particular details, like, so really how many control signals are required. Don't count and tell me, sir, here we require 5 control signals, because already I have seen circuit. In that circuit, we require 5 control signals. Forget about that. We are talking in an abstract way. That means, we are not talking about a particular machine now. So because already you know the concept, right? Just try to, interpret it in a high level. That's why don't go into particular details. Example, to perform fetch operation of any instruction, whenever I say that you require only 3 control signals, simply believe it. Okay, assume that such circuit exists. So assume that, let's say, there are only 10 control signals. Okay, again it's an assumption. I am working on one hypothetical machine which has only, otherwise let's take 64 control signals. Okay, C1, C2, C3, so on, C64. So there are only 64 control signals you might require at any time, but not all at a time. Some of them, correct? Especially for fetch operation, out of that 64, we require C1, C2, C3. Sir, I am not understanding what is control signal. Then recall. In the RISC architecture, already we have seen one particular machine, right? In that PC enable, PC select, right? Multiplexer selection, all that are control signals. So here for fetch, I am assuming that you require 3 control signals. Let us say C1, C2, C3 out of 64. Then what we are going to do is, we are going to program it. That means in the memory. Don't ask me where are you storing this, this storage. Somewhere. Assume that it's a memory. Maybe it's not main memory. Generally it will be stored in random, read only memory, ROM. Okay. So we will see that detail later. At this moment, some memory. In the memory, so somewhere I am taking one row. In that row, I will be writing like this. I will be writing a 64-bit information. So first bit indicates about C1. Since C1 signal is compulsory for fetch, I write like this: 1, C2 1, C3 1, all that 64 other signals should be off. This is called micro instruction. So whenever this micro instruction is executed, that means whenever I take this and I execute it, that means the appropriate signal should be generated. Executing this micro instruction means this is one micro instruction. Okay, if you execute it, then because of these 3 bits ones, C1, C2, C3 should be generated. Such a way, again you have to design a circuit, a little bit circuit. Okay, not a big deal. Now second thing, After fetch we have to do decode, right? Assume that for decoding some 7 signals are required. They are C3 to C9. Okay. Then what is the micro instruction for that decoding? For decoding, micro instruction will be like this. I am writing here. C1 0, C2 0, C3 yes, C4 yes, C5, C6, C7, C8, C9 followed by all the remaining bit zeros. In that way we have to generate 64-bit micro instruction. Now after fetching and after decoding, some more steps are required to execute one particular instruction. Let us say that some other parts of the execution is like this. We need fetch and decode. Now example, let's say you want to execute add instruction here, which I have shown, right? Example this one, add R1 memory of 100 memory of 200. To do that, what extra you need is whatever it is. Let us say, so for that you require some control signals, correct, and some operations, and 5 more operations. Let's say you require 5 more micro instructions, let us say. Okay, 5 more micro instructions. So let us say that micro instructions are 1 2 3 4 5. Okay. Now sir, who is going to do all this stuff? We will be doing. If you are a designer of this architecture, then by after understanding this instructions model and after understanding your machinery, you know your machinery, right, your circuit, and you know your instruction execution model. So simply understand your circuit and understand your instruction model. Based on that, just now I see how you have created a micro instruction for fetch and decode. In the same way, for all other 5 more micro instructions, okay, so which are part of execution of your total add instruction, we have to write a code. Okay, so that is enough. We are not seeing the complete details, like how to write exact code doesn't matter for us, and especially for gate you don't really require. Okay, it depends on the architecture and everything. So we are understanding in again high level. So that's why finally this micro instruction, and these 5 micro instructions, if you executing micro instruction is very simple. Take that word that is called control word, and based on the positions of ones you generate appropriate signals. Finally, end of the day, what are we doing? We are generating the control signals. What is the difference between hardwired and this one? In the hardwired, the circuit was automatically generating the signals. Such a way we created a complex circuit, but here we are programming it, right? So in that way, these are all instructions in the program. Now I can say that here what finally we realized is, you have micro instructions, correct? To execute any instruction you require some set of micro instructions. Especially for add, I said you need 7. It may be true, may not be true. Just for understanding purpose I am assuming 7. Maybe some, it depends on the exact implementation. Second one, the set of micro instructions, if you gather, okay, like this 1 2 3 4 5 6 7, which forms all the control signals required to execute one instruction, that is called microprogram, okay, or micro routine. So this is the micro routine for add instruction. Similarly, there will be a micro routine for load instruction. Similarly, store instruction, correct? So finally what I want to say is, so every instruction, to execute it we need one micro program, correct? Now the important thing which we have to talk about is, what is the structure of this micro instruction? That means if you have micro instruction, is it sufficient or anything else? We will see that details. So let me elaborate these details. So finally, fetch routine and decode routine, that means let me use routine word here. So fetch and decode routines are required for every instruction. Now we can feel like this. So maybe for add instruction this is the micro routine, and maybe for I can say store instruction, that means remaining part of store instruction, this is the routine. In that way, for load instruction maybe this is the routine. In that way you can imagine. Okay. Now sir, what is this control address register, sir? I will tell you. What is this micro program, what is this micro program counter? I will tell you. First of all, you should understand one thing. Whenever you have an instruction, the instruction execution should start with fetch, right? That's why automatically control should go to the starting address of the fetch routine, correct? Assume that let's say fetch is located in this memory at 100. Then initially your micro program counter should show 100. Now example, let's say your instruction is add. For executing add instruction, what should happen? Fetch should be executed. For that, appropriate control signal should be generated. For that, this micro instruction should be executed. After that, this micro instruction, which is related to decode. Later, the control should come to, let's say add starts at 200. Then automatically micro program this counter should show 200. For that, what we have to do? What is the logic? So how to plan so that micro program counter shows exactly the address of the micro instruction which we want to execute, right? It depends on the instruction. If the instruction is store, what should happen is, example, let's say stores remaining in routine starts at 300. What should happen, you know? So in store also, first of all, we have to fetch the instruction. That's why the appropriate control signals are these signals. After that, decode instruction should be generated. After that, we have to generate instructions or control signals related to load store instruction, correct? So can I say one thing? Automatically control should come to the first micro instruction related to store part. So that is the way it should happen, right? Assume that let's say these 4 micro instructions are related to this store instructions, micro instructions. So that whenever this micro word or micro instruction, this and this, if these micro instructions are executed, executing them is nothing but taking that micro instruction and generating the appropriate signals. Finally, already I told you one thing. End of the day, executing our instruction is nothing but generating appropriate control signals. That is what we want. But we are doing with that program. For that, see some of the control signals which are common for every instruction are here, and the remaining signals which are special to a particular instruction are stored as a program for every instruction, correct? So that's why I can say that this area is micro program related to add instruction, and this is micro program related to store instruction, so on. In that way, for every instruction there should be one micro program, correct? Apart from that, what you want? Sir, why this control address register you did not tell us? I will tell you. So what happens is, this micro program counter, of course it is not required, but if we have this, so how we are going to use it, I will tell you. Initially, let's say you are in the early morning, what happens? Your micro program counter can be loaded with 100, so that we can start doing we can start generating the control signals related to fetch instruction. For that, what we do is, initially always whatever we have in micro program counter, we keep that in control address register. We can use this control address register to index this memory. If control address register shows 100, then we will be indexing the memory location at 100. If this control address register shows 200, then we will be indexing 200. In that way, control address register can be used to access the memory. Now, why this micro program counter? This micro program counter always, is going to, this we can use for sequencing. Okay, so here, I mean, we are using 2 registers, but with one also we can do, but I am just showing with 2. Okay, doesn't matter. So this is for sequencing. So every time, example, let's say 100, I will tell you one possibility. Just focus on add instruction. So for add instruction, the instruction to be executed is, micro instructions to be executed is 100, 101. After that, control should come to 200, then 201, 202, 203, let's say 204. That is what my assumption. These are the micro instructions related to your add instruction. For that, your program counter should go like this: 100, then 101, then 200, then 201, then 202, then 203, then 204. Here I am assuming that this memory is word addressable. That means for every different word I am giving one number. So this is the way my program counter or micro program counter should be sequenced. Okay. So we use micro program counter to show the order of the sequence of execution of the program, micro program. and always control address register we use to index, that means to identify the right memory location to fetch the instruction. Okay, in that way, so this register is separate, this address register can be separate. Okay, in that way we can plan. Just remember that. Now the question is, sir, how you change your micro program counter appropriately so that after 101 will jump to 200? Sir, how do you know that we have to jump from 101 to 200? And sir, if it is store instruction, you have to jump from 100, then 101, then 300, not 200, correct? But how do you plan it? Further, in this model, how they planned is, they have, focus on this instruction. The next instruction is generally stored in micro word. Let us use a word called micro word. All these are all words. So each word, because we are storing here all the words, these words are nothing but micro instructions, right? That's why let us use a word called micro word. So each micro word or micro instruction contains two things, I can say. So conditions appropriate for doing some operations. Second one, next address, correct? Since next address is not always immediate one, sometimes it is jump, there is a jump, that's why one more field is required in the word, that is next address. Okay, now from now onwards that will be the usage. Second one, sir, what is this control data register? I'll explain. So whenever you specify any address in control address register, so this memory can be designed such a way that whenever some address is specified, automatically the appropriate data will be selected and that will be automatically transferred to this control data register. So this control data register is used to hold instruction, okay, which currently you are processing. Understand? So example, let's say at this moment initially micro program counter is 100. Then when you want to execute the micro instructions, so 100 will be first of all transferred like this. Okay, such a way we have to plan the circuit. There should be extra circuit that should do it. So 100 should be moved here. Then immediately because of that, this micro word will be fetched. Correct? Now already I told you, whenever you specify 100 here, we have to design our circuit such a way that automatically this memory, whatever the word we have, it should be transferred here. Okay, let us transfer here 1 1 1 0 0 0 0 0 0 something up to 64 bits. Then it is remaining field is next address. Okay, so here we write the next address. Maybe you can write next address 101, so that what is going to happen is, first of all, there will be some extra circuit, we will see the details later. So because of this pattern, appropriate control signals like C1, C2, C3 will be generated. Such a way we have to plan. Okay. Now C4 to C64 should not be generated. That means their bit should be 0. Now the next address 101. That means this should be copied to micro program counter. Now in the next cycle, what happens? Control address register gets 101, and because of that we fetch what? This instruction. Then again that will be transferred to control data register, and again this part will go to control signals. That means, so appropriate control signals will be generated using the micro instruction, otherwise this control word, and this next address we will be using for the next instruction. Might be you have to write like this. After 101, where we have to go? We have to go depends on the instruction, correct? Maybe for add instruction or maybe load instruction, we don't know, right, where to come. So you tell me, after executing this fetch and decode, how you decide whether it is next is add instruction or store or load, correct? So that's why what I want to tell you is, we have to take the input from your opcode of the original instruction. That's why, so let me show here. This is your program counter, micro program counter. So first of all, I show complete idea. Example, let's say your instruction is add. Then first we have to fetch it. That's why micro program counter initially should show 100. So recall, executing add instruction is nothing but doing a stage called fetch stage. After that decode. After that remaining instructions are micro operations. They are nothing but add routine, correct? So finally we have to generate signals for fetching signals related to decode, signals related to add routing, correct? So what I want to tell you is, for that if you observe the machine in this memory addresses, so your micro program counter should start at 100, then 101. That's not a big deal for us because we can store 100 here, 101 here. After that we can write next address, correct? But after 101 we should go where we have to go for 200. But how you decide? That's why your micro program counter is generally also connected to one more thing. That means your micro program counter should take input from two things. One is from here, that means next instruction, next address. Second one from the opcode of your instruction. So where is your instruction? Recall, it is in instruction register, right? So in the instruction register there will be opcode part, right? So using that opcode we have to somehow decide that the next instruction is 200. Okay, so what we have to plan is, so by seeing the opcode of the instruction, somehow you should be able to differentiate what is the starting address of the original routine. Example, let's say it is store. Where store is starting? 300. We have to plan a circuit such a way that if this opcode is opcode for store, then automatically micro program counter should be filled with 300 so that we can come here. In that way we have to plan. So yes, it's not a big deal, correct? So for that we should have a decoder. That decoder should take opcode as input and it should generate memory addresses properly. If the opcode is add, it should generate address 200. If opcode is store, then it should generate 300. In that way, one circuit we have to plan. So that what happens, then your micro program counter will be properly sequenced, correct? That is what our goal. Now, so slowly you realize that your micro program words, if you see micro instructions, what should be the structure of your micro instruction? Micro instruction should contain at least two parts. One is for generating the control signals, correct? So this part is going to generate the control signals. Second part is sometimes showing next instruction. Okay, so that is about this micro program instructions. Now we'll see more details about this micro program control unit. So for that there are two things actually: vertical micro program control unit, second one horizontal. So what is the difference between horizontal micro program and vertical micro program, we will see. Okay, so now we'll see the classification of micro instructions. Actually we can implement this micro programming in two ways. So based on the micro instruction type. So one is vertical micro instructions, second one horizontal micro instructions. If you use vertical micro instructions, then we say that is vertical micro programming. So if you use horizontal micro instruction, then we can say that is horizontal micro programming. However, both are micro programming, but there is a difference between vertical micro instructions and horizontal micro instructions. We will see that. So let's say this is whatever you have studied so far is actually horizontal micro instruction. So where there is an alternative called vertical micro instruction, I will tell you. So whatever so far I have explained you, that is vertical micro instruction. Vertical micro instruction will have two components. One component it generates control signals. Second component will sequence the next instruction. That means after that next set of control signals are where, that will be decided by next instruction, right? So this is called horizontal micro instruction. Now the drawback of horizontal micro instruction is, here example, let's say in your machine there are 64 control signals. That means there are 64 places where we can generate the signals. Okay, example, did you remember? Just for clarity I am giving, for multiplexers, for every multiplexer in your circuit we have to have one signal, right? Similarly for program counter there is a signal called program counter enable, right? In that way. So these are all control signals. Assume that one hypothetical machine has 64 control signals. So then if there are 64 control signals, we don't know which signal should be activated at any point of time. That's why each word, if you see each word, so this portion if you focus, this is micro instruction, right? So each micro instruction, if you say here to here, should have 64 length, correct? Because to generate 64 signals at sometimes you might require to generate 64 signals at a time. then 64 bits are required, right? Minimum 64 bits. So that is what we have done in horizontal micro instructions. So now if you see, sir, what is the problem here? You have 64 control signals to generate them. So 64 different entities are required, right? So but the problem is when you have 64 positions like this for next instruction, sir, what is the size of next instruction? By the way, I will tell you. That depends on your control memory, right? So assume that let's say your control memory contains some, it depends on your micro operations. Assume that there's, let's say this memory size is 256 words, okay, 256 words. To uniquely differentiate the 256 words, then how many bits are required? 8 bits. So there are 256 different locations. To identify them, 8 bits are required. So overall your control word, I can say this entire thing is control word. So the size become 64 plus 8, 72, correct? Otherwise your complete micro instruction word, entire thing is 72 bits, right? Can we reduce it is the question. If you can reduce it, then probably we can reduce the space of this memory, because this memory is precious, because we are going to embed this entire memory in a chip, a small chip which is close to CPU, right? So that is what we are not going to store this entire data whatever we have in main memory. We are not storing in main memory, we are not storing in disk. If that is the case, then you don't bother, otherwise you don't require to bother about saving the space. Since you are creating this memory or designing this memory which is related to CPU board, right, then the size should be as less as possible, okay, so that if the size is less, even the accessing also will be speed. That's why my target is reducing this control memory size. How to do that, sir? By reducing the number of bits for control signals. Sir, how can you do that? Because 64, even your machine, it requires 64 control signals sometimes. But there is a trick here. Though there are 64 positions where you require signals, so they might not be, generally the experience says that generally you might not require all the signals at a time, okay. So example, see the situation. Out of 64 signals, let's say you require only one signal at a time. That means, so depends on the micro operation. In one micro operation you have to enable only, otherwise you have to assert only signal C1. There is a second micro operation. So that micro operation requires only enabling or asserting signal 2 or C2 in that way. So each instruction, micro instruction, require only generating at most one signal, let's say, okay, otherwise exactly one signal, either C1 or C2 or C3, so on. Then how many different patterns are required? Still we use horizontal model first of all. So maybe you require this pattern where C1 is on, all other bits are off, right, like this. So this is one possibility. Second one, you get this binary pattern 0 1 0 0, all the remaining zeros. So each one, let's say 64 bit word, right, 64 bit. But you see, since my assumption is at a time at exactly one signal should be on, then how many different combinations are possible? Only 64, you know that, right? Only 64. Then what we do is, rather than using 64 bits like horizontal micro instruction, we can do some optimization here. What is that optimization is? Only use 6 bits, okay. Now use a decoder, and in digital you have studied decoder. So this decoder can take 6 bits as input and it can generate one of the 64, like it can generate 64 patterns. Such a way we can design a decoder, right? So if you give 6-bit input, then it can generate 64 different signals, okay. So I mean it can generate one of the pattern out of 64 in that way. So we can generate, I can say, 6 to 64 decoder. So what is going to happen because of that? That 6 bits will be converted to one of the 64 patterns. Understand? Example, let's say same thing I will explain for 4 bits. Example, let's say you have 4 signals, okay, 4 signals, but at a time only one signal is active. Then how many different patterns are possible? Maybe 0001, 0010, 0 1 0 0, otherwise 1 0 0 0, correct? Only 4. Then we can create a decoder which will take 2 bits as input, right? So that is going to be any 2, right? So example, let's say 0 0 0 1 1 0 1 1. What we have to do is we have to plan this decoder such a way that when the input is 0 0, then it should generate 0 0 0 1. If the input is 0 1, then it should generate 0 0 1 0. If the input is 1 0, it should generate 0 1 0 0. If the input is 1 1, it should generate 1 0 0 0. In that way, we can plan a decoder which is 2 by 4 decoder. 2 patterns are converted to 4 patterns, right? So, I mean 2 bits are converted to 4 patterns. Yes, it is possible. Understand? But the only thing is, again you require a decoder circuit that will have some delay. That's why here generate. Now how to generate that 64-bit code word we will see. We will be having now control word like this. In that this will be 6 bits. This will be next address. Okay. Next address is as it is, we are not disturbing. But these 6 bits are connected to a decoder. That decoder will generate one of the 64 patterns like original one, right? Now before this decoder we used to have 64-bit patterns directly, but here now from now onwards in the memory we are only maintaining 6-bit pattern, but later when you execute the instruction, that means whenever you take the word from the memory, after taking that from the memory we have to connect it to decoder and we have to generate a 64-bit pattern. Understand? So sir, every time we can do it, right? So why only for this example? Because here you have only 64 patterns. Now let us try to use the same thing. Example, let's say, see this scenario. You have 64 signals, but you don't have clue which signal will be generated at what time. Okay, at any time, any number of signals can be active. Let me clearly write it. At any time, at any operation, okay, any signal can be active. In any operation, any signal can be active. Signal can be active. If that is the case, then how many patterns are possible? If that is the case, it's like a mathematical problem. You have 64 signals, right? 64 bits. At any time, any bit can be active, then 2 to the power of 64 combinations are possible. Why? I will tell you. Let us solve this problem for 3 bits. Example, let's say you have only 3 signals. At a time, any number of signals are active, then how many different patterns are possible? Maybe 0 0 0, no, nothing active, 0 0 1, 0 1 0, 0 1 1, everything is possible, right? Then you get 2 cube possibilities. Now your decoder to generate 2 to the power of 3 possibilities, it requires 3-bit input. Here also to generate one of the 2 power 64 possibilities, then your decoder requires, recall, so your decoder to generate 2 power 64 possibilities, it requires 64 bits. So that's why we can't do any optimization. This will be the best one, right? So, but generally it is not the case. Generally what is the case? Though you have lot of control signals, we don't really require everything at a time. Understand? Example, I mean, I can relate it to your, you know, your daily activity also. Okay, in your life, generally, maybe you have lot of devices, right? You have phone, you have TV, you have fridge, right? You have laptop, in that way. But you tell me, at a time, how many devices you use? At most one, right? So similarly here also same thing. That is what I am saying. Here also, in that case, if example, though you have lot of signals, only few signals are present in this bit, I mean in the word, then we can go for optimizing by using vertical micro instruction, correct? So this is about horizontal versus vertical. Now, using this point, there are a lot of gate questions. We will solve them. So by that time, you understand everything. Now, let me compare these 3 ideas. First of all, we started with what? Hardwired control unit. We have designed control unit by using hardwired, right? Hardwired mechanism. Second one, we have designed control unit using horizontal microprogramming, correct? Microprogramming using horizontal. Third one, we have used microprogramming using vertical. Which one is fastest? and why it is fastest? You tell me. Definitely the circuit will be faster, right? Why? I will tell you. So in the memory model, we are taking example in the circuit model. What were we doing? Example, to perform one micro operation, automatically at that time that circuit was generating the signals. But here what is happening? To perform one micro operation, then we have to go to one word, micro word, right? We have to take it and we have to keep it in, your control data register. After that, we have to generate the signals, correct? For that we have to give it to, circuit again. So there are two levels, right? First of all, we have to fetch the instruction from the memory. After that we have to generate the signals, but here directly circuit itself is generating the signal. That's why hardwired control unit will be faster than horizontal, otherwise microprogramming. First of all, now we'll compare horizontal versus vertical. Which one is faster? Definitely horizontal. Why? Because in horizontal, directly after fetching the instruction, micro instruction, we are simply generating the signals, right? But in vertical microprogramming, after fetching the micro instruction, we are not directly able to, we were not able to directly generate the signals, because we will be using compact form, correct? Because of this compact form, what happens? We have to give that to a decoder again. So that decoder has to generate the control signals, right? So that's why I can say that again there is a delay because of the decoder, one more level. So that's why, so the fasterness, if you see, definitely hardwired is good, then horizontal, then microprogramming. So vertical microprogramming is the slowest one, right? Sir, why then people still prefer hardwired faster? Then second question, sir, why people don't prefer hardwired? In which cases we should not prefer hardwired? The problem with hardwired is, suddenly you want to add a new instruction, then we have to collapse the circuit and we have to start from the scratch. And at the design level, once you design a circuit, if you want to do any modification, it will be very difficult. But in microprogramming, if you want to add any new instruction, okay, otherwise if you want to add any new control signals, and if you want to, why we want to add new control signals? Maybe you want to add new equipment to your circuit. When you add new equipment and new signals, then we can change the program. That means, in the memory, what you do is, I will tell you in the high level, this is your memory, right? Directly go to memory and modify some of the bits. Example, you had a new signal and you want to generate a new signal in some particular instruction. Then you change the program. By changing the program, we can generate more signals and new signals and whatever we can do, right? It's like a software kind of thing. So if I ask one question, which one is good, like hardware or software? Definitely software will have flexibility. Similarly here also, because of the software, I can say, not exactly software, it is called firmware. So this memory model, whatever you are using, because of that you get flexibility, but at the cost of speed. Now sir, what is the difference between vertical and horizontal? Where is the difference? The only difference is you are using compact form in the vertical micro instructions. Because of that, it is adding more delay. But what is the advantage it is giving? It is reducing your memory size, correct? So we are going to keep all the micro instructions in memory. So if you take vertical micro instruction and horizontal micro instruction, which one will be relatively lengthier? Definitely horizontal, correct? So vertical micro instruction will look like this, correct? Because of that, then what is going to happen? We can reduce because we are going to keep these instructions in the memory, so memory size will be decreased. When memory size is less, then access will be faster. That is what the idea. So that sometimes you might not have that much space which is near to your CPU, correct? That's why we have to always reduce the space requirement. That's why we go for vertical micro instructions. But again, trade-off. When you go for vertical, then we require one more level of decoding. Because of that, it will become slower. Understand? This is all about control unit design, right? Initially, let us summarize. Initially we started with what? Just circuit, right? Your processor, and we have understood processor and how to design it, right? Like we have seen data path also. After that, after data path, what I taught, after that I slowly explain you that we need signals, control signals to activate at appropriate times for proper execution of the instructions. But how to generate the control signals, for that we learn control unit design. Control unit is going to generate control signals. We can do with three techniques. One is hardwired, second one microprogramming. In microprogramming we have horizontal, second one vertical. This is all about control unit and instructions design, right? So now what we do is we solve a lot of gate questions. Now I hope definitely if you attend these lectures up to this point, every gate question you will be answering from hardwired, I mean any control unit. Okay.